So, welcome to a lecture series on mathematical methods and applications. So, we have seen what Fourier transforms are, and also we have seen Fourier sine and cosine transforms. So, how can you write Fourier transform of function f t? Fourier transform of a function f t is given by minus infinity to plus infinity f t e की power minus eta omega t into d omega into dt, okay, and we are calling it f omega, function of omega. So, and the inverse Fourier transform of f omega is f omega is given by it is 1 upon 2 pi integral minus plus infinity, it is f omega e की power eta omega t and it is d omega. So, which is nothing but f t. So, this we have already discussed, and this comes from complex form of Fourier integrals. This we have already seen that Fourier transform f t is nothing but given by this expression, and the inverse Fourier transform is given by this expression. Now, let us come to convolution theorem for Fourier transforms. So, before discussing convolution theorem, let us discuss some more properties of Fourier transforms. So, first of all, Fourier transform of derivatives. Okay. So, let f t be continuous on the x axis and f t tending to 0 as mod t tending to infinity. Now, further suppose f dash t is absolutely integrable on the x axis, then Fourier transform of f dash t is given by eta omega Fourier transform of f t. So, this thing is very easy to prove, Fourier transform of f dash t. So, by the definition of Fourier transform, it is nothing but minus into plus infinity f dash t into e की power minus eta omega t into dt. So, this will be nothing but, let us suppose it is first function, is second function. So, first as it is integral of second function from minus into plus infinity and minus integral derivative of first is minus eta omega into e की power minus eta omega and integral of second, which is f t into dt. So, this is by integration by parts. Now, as we have assumed that as f t, as mod t tending to infinity, f t is tending to 0, that is when t is tending to plus or minus infinity, f t is tending to 0. So, from the upper and the lower limit, this is tending to 0. So, this is nothing but 0 plus eta omega times minus infinity plus infinity e की power minus eta omega t into f t dt. Now, what it is? It is nothing but Fourier transform of f t. So, it is eta omega times Fourier transform of f t. So, hence the Fourier transform of f dash t is nothing but eta omega times Fourier transform of f dash t. Now, suppose you want to find out Fourier transform of f double dash t. So, you simply replace f by f dash in this expression. So, that will be nothing but eta omega Fourier transform of f dash t, which is equal to Fourier transform f dash t we already derived is equal to this expression. So, this is nothing but eta omega whole square Fourier transform of f t. So, in the similar way, if we proceed for the nth derivative for the same expression, so we get Fourier transform of nth derivative of t will be nothing but eta omega की power n Fourier transform of f t. So, nth derivative of Fourier transform of f will be nothing but eta omega की power n Fourier transform of f t. So, this is how we can obtain Fourier transform derivatives. Now, let us solve these two problems. Find Fourier transform of f t where f t equal to this. Okay. Find Fourier transform of f t actually. So, we have to find Fourier transform of t e की power minus t square. Okay. Now, this is nothing but Fourier transform of e की power minus t square is derivative. Its derivative is nothing but minus 2t times this thing. You multiply and divide by this expression. So, this will be nothing but when you simplify this, So, you get back this expression. Now, by the Fourier transform derivative, we know that Fourier transform of f dash t is nothing but eta omega times Fourier transform of f t. So, this is nothing but minus half of eta omega times Fourier transform of e ki power minus t square. Because here f t is e ki power minus t square, its derivative, and its derivative is given by eta omega Fourier transform of f t. Okay. So, this is this expression. Now, let us find Fourier transform of E t square. So, Fourier transform of E t square, Fourier transform of e ki power minus t square will be given by the minus plus infinity f t into e ki power minus eta omega t dt, which is equals to minus plus infinity e ki power minus. So, when you make perfect square, it is t plus eta omega by 2 whole square, a square plus 2ab and minus eta omega by 2 whole square into dt. So, which is equal to, it is minus minus plus, it is e to the power minus omega square by 4 can come out because it is free from t, and it is integral minus plus infinity e to the power minus t plus eta omega by 2 whole square into dt. Now, you can take t plus eta omega by 2 as suppose under root p, okay, or you can take it as, suppose you can take it as z first, okay. So, then dt will be nothing but dz. So, it will be e ki power minus omega square by 4 minus mu plus infinity e ki power minus z square into dz, limit will remain the same, okay. Now, it is an even function. So, this can be written as 2 times e ki power minus omega square by 4 0 to infinity e ki power minus z square dz, okay. Now, we can let z equal to suppose under root p. So, this will give, this integral will give, Fourier 2 e ki power minus omega square by 4 integral 0 to infinity 1 by 2 under root p e ki power minus p into dp, okay, which is nothing but 2 cancel out, and it is e ki power minus omega square by 4, and it is gamma half by the definition of gamma function. So, this is nothing but under root pi e ki power minus omega square by 4. So, therefore, the value of this is nothing but minus 1 by 2 eta omega under root pi e ki power minus omega square upon 4, okay. So, here we use the concept of derivative of Fourier transforms. And to find out Fourier transform of e ki power minus t square, we go back to the main definition of Fourier transforms. There we simplify and we get the Fourier transform of e ki power minus t square, okay. Now, suppose you want to solve this problem, okay, the next problem. It is y dash minus 2y will be equal to e ki power minus 2t u naught t, okay. Take Fourier transform both the sides. What is the Fourier transform y dash? By the formula, it is eta omega f omega, where f omega is the Fourier transform of yt, minus 2 Fourier f omega, and is equal to, we already know that Fourier transform of e ki power minus at u naught t is a unit step function at t equal to 0. We already know that the Fourier transform of this is nothing but 1 upon 2 plus eta omega, because Fourier transform of e ki power minus at u naught t is 1 upon a plus eta omega, okay. So, what we obtain from here? We obtain that f omega is nothing but 1 upon eta omega minus 2 into 2 plus eta omega. When we simplify this, so this is nothing but a square minus b square, and which is equals to minus of 1 upon omega square plus 4. Now, we have also seen that Fourier transform e ki power minus a mod t is nothing but 2a upon a square plus omega square, that we have already derived. Okay. So, it is something like 1 upon omega square plus 2 square. So, you can multiply and divide by 4. So, minus 4 into 4 upon omega square plus 4. So, instead of a we have 2. So, this is nothing but, if we take inverse Fourier transform both the sides, so yt will be nothing but minus 1 by 4, and inverse of this will be given by that is e ki power minus 2 into mod t. So, that will be the solution of this expression, this differential equation. Okay. So, we take Fourier transform both the sides, simplify, and the inverse of Fourier transform will give the solution of this differential equation. Okay. Now, differentiation with respect to frequency omega. Let us suppose function is piecewise continuous on the x axis, and let t ki power n f t be absolutely integrable on the x axis. Then we have a result for Fourier transforms. Then Fourier transform of t ki power n f t, that is multiplication of with t, is nothing but eta ki power n and nth derivative with respect to omega of f omega. Okay. Nth derivative of omega with f omega. Okay. Now, to prove this, the proof is simple. You take d by d omega of f omega. Now, f omega is the Fourier transform of f t. So, it is nothing but d by d omega of minus into plus infinity f t e ki power minus eta omega t into dt, because Fourier transform f t is given by this expression, and f omega is nothing but Fourier transform of f t. So, this will be given by the Leibniz theorem. It is nothing but del by del omega of f t into e ki power minus eta omega t into dt, which is nothing but when you take derivative with respect to omega, it is nothing but minus eta t into f t e ki power minus eta omega t into dt. Now, minus eta will come out, and this is nothing but t f t e ki power minus eta omega t, that will be nothing but Fourier transform of t f t. So, here, so therefore, f dash omega will be nothing but this expression. Now, when you multiply with iota both the sides, so this is nothing but iota f omega will be equals to Fourier transform of t f t. So, hence Fourier transform of this is nothing but this expression for n equal to 1. So, similarly, if you take second derivative, suppose you take second derivative d2 upon dwt of fw. So, that will be nothing but by the same concept, it is nothing but d by dw of integral minus plus infinity. First we take first derivative by this expression del by del w of f t e ki power minus eta omega t into dt. So, that will be given by d by dw of minus infinity to plus infinity eta t f t e ki power minus eta omega t. Again, when you take this d by dw inside and you differentiate with respect to omega, so that will be nothing but minus plus infinity, it is minus eta ka square t square f t e ki power minus eta omega t into dt, which is iota square times integral minus plus infinity t square f t e ki power minus eta omega t dt, and this is nothing but minus Fourier transform of t square ft. Okay. This is nothing but Fourier transform of this. Okay. Now, okay, this implies Fourier transform of t square ft will be nothing but eta square times double derivative of f. Here we have a single derivative, okay, here we have a single derivative and here we have a double derivative. So, so that means similarly if we repeat this process n times, so we will get back this expression that the Fourier transform of t ki power n f t will be nothing but iota ki power n f omega and a derivative of f omega. Okay. So, in this way we will get back this expression. Now, using this, suppose we want to find out Fourier transform of t e ki power minus 2 mod t. So, that will be nothing but using this expression, it is nothing but iota ki power 1 because n is 1 into Fourier transform of into derivative into d by d omega of f omega, where f omega is the Fourier transform of this f t, it is e ki power minus 2 mod t. And what is the Fourier transform of this? It is 2a upon 4 plus omega square. So, this will be nothing but eta d by d omega of 4 upon 4 plus omega square, which is nothing but 4 iota into minus 1 upon 4 plus omega square ka whole square into 2 omega. So, that will be nothing but minus 8 omega iota upon 4 plus omega square ka whole square. So, this will be the Fourier transform of this expression. Now, Dirac delta function, we already defined Dirac delta function in Laplace transform, that it is given by 1 by epsilon when t varying from a to a plus epsilon and 0 otherwise, and where epsilon tend to 0. So, roughly speaking, Dirac delta function is infinity at a point at say t equal to a and 0 otherwise, such that the total integral from minus infinity plus infinity of Dirac delta function is 1, that we have already discussed in Laplace transforms. Now, the Fourier transform of Dirac delta function is given by this. So, this can be derived using the definition of Dirac delta function, I mean Dirac delta and Fourier transform. So, to find Fourier transform of Dirac delta function, it is nothing but minus infinity plus infinity ft is Dirac delta into e ki power minus eta omega t into dt. Now, Dirac delta is given by 1 by epsilon when t varying from a to a plus epsilon, where epsilon tend to 0. So, this we can define like this, limit epsilon tend to 0 a to a plus epsilon, it is 1 by epsilon into e ki power minus eta omega t into dt. Now, it is limit epsilon tend to 0, 1 by epsilon can come out, and the integration of this will be nothing but this term from a to a plus epsilon. Now, it is nothing but limit epsilon tend to 0, okay, 1 upon minus eta omega can come here, and it is e ki power minus eta omega a plus epsilon minus e ki power minus eta omega a by applying upper limit minus lower limit. Now, when epsilon tend to 0, it is 0 by 0 form. So, you will apply L'Hospital rule to simplify this. So, you will take the derivative of the numerator and the denominator. So, limit epsilon tend to 0, the derivative of numerator will be nothing but it is minus eta omega e ki power minus eta omega a plus omega minus 0 upon minus eta omega. Derivative with respect to omega, I mean epsilon. Okay. Now, these two terms cancel out, and when you take epsilon tend to 0, it is nothing but e ki power minus eta omega a. So, which is the same as this expression. Okay. Now, when you take a equal to 0, it is clear that when you take a equal to 0, Fourier transform of Dirac delta t at a equal to 0 is nothing but 1. So, this is very clear from this expression when you substitute a equal to 0. Now, come back to convolution theorem. Now, convolution of two functions defined in the same way as we did in Laplace transform. Now, here integral is from minus into plus infinity. So, convolution of two functions in Fourier transforms is given by this. So, convolution of two functions in Fourier transform is given by minus into plus infinity f tau g t minus tau d tau, or can be written as minus into plus infinity f t minus tau g tau d tau, because this convolution of two function is commutative. Okay. Now, come to convolution theorem. Now, what it states? Convolution theorem for Fourier transforms. Suppose that f t and g t are piecewise continuous, bounded and absolutely integrable on the x axis. Then Fourier transform of convolution of two functions f and g will be given by Fourier transform of f into Fourier transform of g, which is nothing but f omega into g omega. So, we are Fourier transform f t is of omega and Fourier transform of g t is g omega. So, now we will see the proof of convolution theorem. So, basically want to find out Fourier transform of f star g. Okay. So, by definition it is nothing but minus infinity plus infinity convolution of this function into e की power minus eta omega t dt. This is by the definition of Fourier transforms. Fourier transform of function f t is given by minus infinity plus infinity f t e की power minus eta omega t dt. Now, convolution of two function, this term is given by, you replace this term as minus infinity plus infinity, suppose f tau g t minus tau d tau and whole multiplied by e की power minus eta omega t into dt. So, this can be written as minus infinity plus infinity f tau g t minus tau e की power minus eta omega t d tau into dt. Okay. Now, change the order of integration. Both the limits are constant, minus plus infinity. So, change the order of integration. So, when you change the order of integration, nothing but minus plus infinity f tau g t minus tau e की power minus eta omega t dt into d tau. Now, suppose t minus tau as a new variable, suppose z. So, dt will be dz. Okay. So, when you substitute this variable over here in this expression, so what we get? So, basically we are simplifying Fourier transform of convolution of two function. So, that will be equal to this expression, and this will further be equal to minus infinity to plus infinity, this is f tau and this is g z e की power minus eta w, and t is nothing but tau plus z from this expression, and dt is dz and d tau is d tau. So, this is nothing but, now you can write it like this, minus plus infinity f tau e की power minus eta omega tau d tau, because now you can separate two variables are separating, tau we can write separately and z we can write separately. So, we can always do this, and this is nothing but Fourier transform of f t, and this is nothing but Fourier transform of g t. So, this is nothing but f omega into g omega. So, hence Fourier transform of convolution of two functions f and g is nothing but f omega into g omega. Okay. So, this is convolution theorem, and here is the proof. Now from here it is also clear that when the Fourier transform of f star g is f omega g omega. So, from here we can write that f star g into t is nothing but Fourier inverse of f omega into g omega. Now, inverse Fourier transform is given by 1 upon 2 pi integral minus infinity plus infinity the omega function which is f omega into g omega e ki power eta omega t into d omega. So, that we already know by definition of inverse Fourier transforms. Okay. Now, let us find Fourier inverse Fourier transform of this f omega using convolution theorem. Okay. So, how we can do that? So, we will recall convolution theorem again, and using convolution theorem we will try to find out the Fourier inverse Fourier transform of this function. So, what is the function now? What we have to find out? Fourier inverse of 1 upon 6 plus 5 eta omega minus omega square. So, this is f omega. So, this is f omega. So, f omega is nothing but 1 upon 6 plus 5 eta omega minus omega square. Okay. So, in order to apply convolution theorem we have to write as a product of two omega functions, and the Fourier inverse of both the omega functions we should know. So, that convolution theorem we can apply. Okay. So, let us try to write this function. So, we can easily write it as 1 upon 6 plus 5 eta omega plus eta square omega square, and this is nothing but we can simplify. When we simplify, so this is a square plus 5a plus 6. So, this is eta omega plus 2 into eta omega plus 3. So, this is nothing but 1 upon eta omega plus 2 into 1 upon eta omega plus 3. So, this is something like g omega and this is something like h omega. So, we have write this f omega as a product of two omega functions. Now, to find out its inverse using convolution theorem. So, f inverse of f omega which is equals to f inverse of g omega into h omega will be equal to. So, we will apply convolution theorem. It is nothing but convolution of this and this. So, what is Fourier inverse of g omega? So, Fourier inverse of g omega we know that Fourier inverse of this is nothing but e ki power minus 2t u naught t. This we already know, and Fourier inverse of this expression 1 upon Fourier inverse of h omega. H omega is this, is nothing but e ki power minus 3t u naught t. Okay, this is by the, this we already know that Fourier transform of e ki power minus at u naught t is 1 upon a plus eta omega. Okay. Fourier transform of f omega which is equal to Fourier inverse transform of f omega into g omega here using convolution theorem will be nothing but convolution of these two functions e ki power minus 2t u naught t star with e ki power minus 3t into u naught t, the convolution of these two functions. Okay. And that will be nothing but minus infinity plus infinity f tau, it is e ki power minus 2 tau u naught tau into g t minus tau, it is 3 minus 3 t minus tau u t minus tau and it is d tau. Okay. This is by the convolution theorem because f tau into g t minus tau. Okay. Now, let us simplify this. Let us simplify this. Now, here we have two unit step functions here and here. So, let us find what it is. So, it is u naught tau into u t minus tau. So, now we have to see d tau. Tau is a variable basically. So, we have to see with respect to tau. So, when tau is less than t, okay, and suppose greater than 0. So, when tau is less than t, this quantity is positive because tau is less than t, okay, and this is also positive. 1 into 1 is 1, and when tau is greater than t, so this is 0 because this is negative, this will be 0. So, when we apply this over here, so this will be equal to, now e ki power minus 3t is free from tau, can be come out, and it is e ki power minus plus 3 tau into e ki power minus 2 tau is e ki power tau, and this product is 1 when tau varying from 0 to t, otherwise it is 0. So, it is from 0 to tau, from 0 to t only, and it is d tau. Okay. So, this will be equal to e ki power minus 3t e ki power tau 0 to t, which is equal to e ki power minus 3t e ki power t minus 1. So, that will be the inverse Fourier transform of this function, this f omega, using convolution theorem. So, hence using convolution theorem we can find out inverse Fourier transforms also. Okay. So, the main application of convolution theorem is to find out the Fourier inverse. So, sometimes we have to find out Fourier inverse, so it is important to use convolution theorem. So, that is all. So, thank you very much.